Hello, good evening to everyone. Welcome back to session 2 of day 13th, GATE 2021. Now, the topic is fluid mechanics and hydraulics, which will be presented by Professor DP Mahesh. Professor DP Mahesh is Associate Professor in the Department of Civil Engineering in Vidyavardhaka College of Engineering. Professor Mahesh completed his BE degree in Civil Engineering from PS College of Engineering, Mandya, and also completed his MTech from PS College of Engineering, Mandya. He has 21 years of experience in teaching and research. His area of interest are environmental engineering, hydraulics and irrigation engineering, fluid mechanics, etc. I'll welcome Professor TP Mahesh for presenting the lecture on fluid mechanics and hydraulics. Over to you, sir.
Thank you, Mr. For the introduction. Now I will going to speak on the topic fluid mechanics and the hydraulics. Fluid mechanics and the hydraulics. So will be the topic for the day. And let us discuss what is buoyancy and the flotation. Buoyancy. So whenever the body is immersed in a fluid, an upward force is exerted by the fluid on the body. This upward force is equal to the weight of the fluid displaced by the body, and that is called buoyant force or simply buoyancy. So because of this reason, the body which is immersed in water, they weigh less. Similarly, there is a center of buoyancy. Buoyancy is a force which is an upward force, and that will be acting on the body when submerged through certain point. The point through which the buoyant force will be called as center of a buoyancy. Center of a buoyancy is a mere point that lies within the submerged portion of the body, through which the buoyant force will act vertically upward. That is called center of buoyancy. Now coming to the meta-center. So similar to center of buoyancy, there is another point in the submerged bodies that is called meta-center. Meta-center is exclusively for the body which floats. Whenever the body, when they tends to float in the water, then there is a definite point about which the body will always oscillate. You can look at the figure. In the first left figure A, you can see there are 2 points G and B, where G is the center of gravity of the body, the whole body, whereas B is the center of a gravity of the portion which is submerged. Both G and B, of course, they are the centroid or center of gravity. The G is the center of a gravity of the whole body, whereas the B is the center of a gravity of the immersed portion of the body. That point is called center of a buoyancy. Now we can see the another figure, the figure B. So whenever a small amount of displacement is given in the clockwise, then the body tends to oscillate like this. The moment when the oscillation displacement is given, then the center of buoyancy, because the volume of the submerged portion of the body will change. Because of that reason, the center of a buoyancy will also change. Then the point B is shifted to B1. Now the point B is at B1 actually, because the submerged volume of the body will change the moment when you twist. So now through the B1, there is a upward thrust will always act, and that line of action it assumed to meet at a point called M. That is the point where the whole the body will oscillate. That point is called metacenter, and which is the most important parameter as far as the floating body is concerned. Now coming to the metacentric height. The metacentric height, so you can see the same figure. So the G and B are the center of a gravity of the whole body, and the B is the center of a buoyancy. Then what is metacentric height? And we know that there is a point called metacenter about which the body will oscillate. Similarly, so when the body oscillate, so the B is shifted to B1. So and that when that is extended, it will point at the point, it will meet the normal axis at a point called M. Now you can see the distance between the point M called metacenter, the point G is called center of gravity, that will be called metacentric height. In order to find the metacentric height, there is a equation. This is the final equation of the metacentric height. That mg means the distance between the metacenter to the center of a gravity, that will be equals to moment of inertia divided by the volume of the submerged portion minus bg, where I is actually y is equal to moment of inertia of the plan of the body about the y axis. Similarly, v is the volume of the submerged portion of the body. So that if you know the high value, the volume value, and the b to g distance, so we can able to find the metacentric height. Now coming to equilibrium conditions. So equilibrium condition means, so you have seen the way in which the boat ships are floating in the sea. So they are not sinking inside the sea. They keeps on floating. The ships are keeps on floating. When we can see the wooden log. When you throw the wooden log into the river or a channel, that keeps floating. So that concept we will explain now. A submerged equilibrium conditions. A submerged or a floating body is said to be stable. Stable means equilibrium. If it comes back to its original position after a slight disturbance, the relative position of the center of gravity and the center of the buoyancy of the body determines the stability of the submerged body. The most important factor here is the position of the G and B that decides. Sometimes G is above, sometimes B is above. Sometimes the G center of gravity will be above the center of buoyancy, and sometimes the point B is above the center, below the center of gravity. So accordingly, we have stable, unstable, and the neutral. So there are two cases we will discuss about it. Floating one. Now coming to the stability of the submerged body. So you can see the figure. So in the figure, just you can look at the figure. So here there is a balloon. You know the balloon. The balloon is one which is completely suspended in air. So you can see the figure. In the leftmost figure, which indicates the balloon is in air. You can and there is you can see the lower end of the balloon where there is a heavy material. So thereby the center of gravity will located near that portion, and B is the point. The B is the point. So where the upward thrust will assume to act. The center of this is called center of a buoyancy. G is the center of gravity, because the balloon weight will attract toward the lower end. Thereby G is below. Then B is the point. When we will call it a stable equilibrium, when W is the weight of the balloon, Fp is the upward thrust. When these two are equal and the point B which lies above the center of a gravity, then it will be called stable equilibrium. So then it will be called as stable equilibrium. So when it comes to the unstable equilibrium, the moment when B and G interchanges, or if the weight, but still W called weight of the balloon and the Fb is called force of buoyancy, they are equal, but the center of the buoyancy, which is below the center of the gravity, then the body is unstable equilibrium. The reason behind here is when you rotate or it rotate in the clockwise direction, then the couple due to Fp and W, the resulting couple due to the force W and the Fb, they are also in the clockwise direction, so that will not keep the balloon in the equilibrium. That's why it is called unstable equilibrium. So now what is neutral equilibrium? There is a case where both B and G are at the same point. So the Fp and W, they are equal and opposite. So depending on the position of the center of a buoyancy and the center of the gravity of the body, so we can say whether the body is in stable or unstable or even neutral. Similar to this, in the previous slide, actually, we explained about the submerged body. So now coming to the floating body. The stability of the floating body, which determines by the single parameter called metacenter. The single parameter is called metacenter. In case of floating body, the weight of the body is always equal to the weight of the body, which is always equal to weight of the fluid displaced. So the body weight will be always equals to the moment when the body is floating, the part of which will be submerged, and we can find its volume and we can measure its weight. The weight of the volume of the water displaced by the floating body will be equals to the weight of the body. Now coming to the conditions of equilibrium. The stability of the floating body, nothing but the conditions of equilibrium. Now, similar to submerged body, we have some condition for floating body: stable, unstable, and neutral. So now see the stable equilibrium. When we will call stable equilibrium, if you can see the figure, if the point M means metacenter, when it is above the center of a gravity, then the floating body will be in the stable equilibrium. So when the body is in stable equilibrium, to which when the small disturbing couple is applied, like in the second figure, when it is applied, then it is in the clockwise direction. The center of buoyancy B, which is shifted to B1 because the volume submerged will be changed. So thereby the center of buoyancy will also change. The B shifted to B1. Then the buoyant force FB, which will act through the new position of B1, or B, it is called B1. Then the weight will act through G, and these two together will constitute a couple. So constitute a couple which will be in the anti-clockwise direction. So thereby, they tends to keep the body in the equilibrium, because when you turn in clockwise, thereby the B will shift it to B1, buoyancy will change, center of buoyancy will change, but through center of buoyancy, that buoyant force will act. Through G, the weight of the body will act. These two together will constitute a couple, but couple will be in the anti-clockwise direction. So though there is a disturbing couple in the clockwise direction, there is a ready anti-clockwise couple, so that these two together will keep the body in the equilibrium. That is called stable equilibrium. Coming to unstable equilibrium. Now look at the second figure. If the point M is below G, there is a case where M will be below the G. When M is below G, then the floating body will be in unstable equilibrium. So the disturbing couple, so you can see, so there is a disturbing couple. The disturbing couple means a kind of a rotation. The disturbing couple is acting in the clockwise direction in the right side figure. So now every time there will be a force through the center of gravity and the center of buoyancy. They together will constitute a couple. It can be a clockwise, it can be anti-clockwise. It all depends upon whether the M is below the G or whether the M is above the G. That is the most important. So now these two together will constitute a couple. That couple is also in the clockwise. Your disturbing couple is also clockwise, so that there will be a overturning. Hence, the body will not be kept in equilibrium. That's why it is called unstable. Now coming to neutral equilibrium. In case of a neutral equilibrium, like in the submerged bodies, here also the point M and the center of gravity are at the same point. Now we have one example. So a body, this problem which speaks about when the body is submerged in water which has a known weight of 962. Actually, when we talk about the weight of the body, there will be two doubts, whether the body weight is in air or the body weight is in water. So unless otherwise specified, the weight of the body is always when it say weight of the body, it is always weight of the body in air. When they very clearly specify weight of the body in water, so you have the specified value. Now it is the weight of the body in water, which weighs 1962 in water. Calculate the weight of the body in water is not equal to the weight of the body in air. The body weight in air, which is always more than what it is in water. Calculate the specific gravity of the body. So here there are 4 options. So now you can look at the solution. So volume of the body. The body is a rectangular one. So we have the 3-dimension length, breadth, and depth. So we will come to know the volume. 1.5 into 1 into 2, 3 cubic meter is the volume of the body. Now weight of the body in water. So you don't write simply just weight of the body. You always mention whether this weight is in air or in water. So it is very clearly specified in the problem. This is the weight of the body in water. That is 1962. Then volume of the water, we know the concept, volume of the water displaced. When this is the volume of the body, actually volume of the water displaced will be equals to volume of the body. Volume of the water displaced, which is equals to volume of the body. So volume of the body is 3 cubic meter. So then what is the weight of the water displaced? Weight of the body is 1962. Then volume of the water displaced is equal to volume of the body, which is 3 cubic meter. Then weight of the body will be, weight of the water displaced will be equals to, that is specific weight multiplied by volume will be the weight of the water displaced. So this much is the weight of the volume displaced. Actually, according to the buoyancy concept, weight of the body in air for equilibrium, weight of the body in air minus weight of the water displaced will be equal to the weight in water, weight of the body in water. So that you will get the weight of the body in air. So that will become 31,392. This is the body weight in air. You can see just what is the body weight inside the water, which is just hardly 1962. And its real weight in air, it is 31,392. The moment when we know the weight of the body in the air, we can able to calculate the mass of the body. Mass basically nothing but that is weight divided by G. Because W is equal to a mass into G, thereby mass equals weight by G. Then weight in air, it is 31,390 divided by G, then automatically the unit converted to kg per cubic meter. This should have been kg per cubic meter. It's not a kg. Sorry, it is 3,200 kg. It's a mass actually. So then coming to density of the body, mass by volume. So far we found mass, that is 3,200 kg, that is in 3 cubic meter. When you divide the mass by the present volume of the body, you will come to know the density, which is per cubic meter. So once the density of the body is known, so we can able to calculate the specific gravity of the body, because specific gravity of any body, by definition, density of the body by the density of the water. Density of the body is 1066.67 and divided by the density of water, which is 1.067. Now the correct answer is the C. C is the correct answer. Now coming to another problem of the same buoyancy concept. A solid cylinder of diameter 4 meter has a height of 4 meter. Find the metacentric height of a cylinder if the specific gravity of the material of the cylinder is 0.6 and is floating in water with its axis vertical. So there are 4 options. So minus 0.3, minus 0.4133, minus 0.3243, minus 0.4323. Let us calculate the correct answer. So this is a solid cylinder of dia 4 meter. We have to write both plan and the elevation of the cylinder. So the figure, which this one indicates the plan, the lower one indicates the sectional view or elevation. So it's a circular solid cylinder. Diameter means it's a circular in cross section. The diameter is 4 meter. So you can see, so in the lower figure, we can show how it is floating in the water. It has height equals to 4 meter. So now, so still we don't know what is the depth of the immersion of the body. So that we can calculate it like this. So depth is 4 meter, height is 4 meter. It is floating in the liquid which has specific gravity of 0.6. So now depth of the cylinder in water, for that we have a formula to calculate the depth of the cylinder in water, that is the specific gravity multiplied by the height of the body. This is a ready formula, that is specific gravity multiplied by the height of the body. That is 0.6 the specific gravity multiplied by the 0.4, the 2.4 meter will be the depth of immersion, depth of the cylinder in water. So only out of the 4 meter, 2.4 meter is inside the water. Sorry, it's not a water. Depth of cylinder is actually a liquid of specific gravity 0.6. So it is not water. 0.6 into 4, 2.4. Now, let the lower end of the cylinder be A. Then G is the center of a gravity of the entire cylinder. Then B is the center of a gravity of the portion which is inside the liquid. That B is actually center of a gravity of the submerged portion. That is called center of buoyancy by a popular name. That is B. Now let us calculate what is A to B. A to B is actually, since B is the center of the submerged part, the total height of the submerged is 2.4, then that will becomes 1.2 from E or from the other end also. So now what is A to G? A to G means it is G is the center of gravity of the real cylinder, which has height equals to 4 meter. That's why it is 2 meter. Then what is B to G distance? The difference. The difference of AG and AB will give the BG distance. That is 0.8. So then coming to moment of inertia. What is moment of inertia? By definition, the moment of inertia, it will be the moment of inertia of the floating body about an axis YY in the plan. About an axis, you can see the plan since it is circular. So about YY or about x-axis for circular section, the formula remains same, which is pi by 64 into d to the power 4. You will get this answer. Now coming to the volume of the cylinder, which is completely inside. So for the volume, to calculate volume, so we must calculate the cross section and multiply by the depth of submersion, depth of immersion. So that will give the volume. So you have to calculate the moment of inertia of the floating body in the plan about an axis called YY. Then what is the volume? It is which is completely submerged, volume of the submerged portion, and also the distance between B. These three values are required in order to find the metacentric height. So because we found BG, we found I, we found volume. So let us substitute all these in the metacentric formula that says that a moment of inertia divided by the volume minus BG. Final answer is minus 0.3833. Then you have minus 0.3833, which is the answer A. Now coming to the channel flow, open channel flow. And in the last session, we have discussed about the pipe flow. So what is the difference between the channel flow and the pipe flow? Pipe flow is one where normally the flow takes place by the pressure. So there pipes are meant to carry the water through by the pressure, whereas open channel flow, most of the open channel are constructed or designed or led to carry the water by the gravity. Now, so open channel flow is by definition the flow of a liquid with a free surface, which is called as open channel flow. Now the pressure at the surface is always atmosphere. Since the free surface, the topmost layer of the water in the channel, which is kept exposed to the air, that where the pressure is atmospheric. Now the flow takes place due to the slope of the bed of the channel only. So most of the cases in the open channel, the flow takes place by the gravity, not by the pressure. Now coming to the classification of the open channel. When it comes to the classification of the channel, open channel, like in the pipe flow here also, we have steady flow, unsteady flow. We have uniform flow and non-uniform flow. We also in the uniform and non-uniform flow, there is another classification called rapidly varying flow and gradually varying flow, laminar and turbulent flow, a subcritical, critical and supercritical flow. So what is steady flow? Steady flow is one where the flow characteristics such as depth, velocity, and the discharge are constant, or they do not change with respect to time. They remain same. So in case of unsteady flow, they keep changing from point to point. They keep changing. That's why it is unsteady. Steady means the velocity, the depth, discharge, and etc. They remain same at any point of time. So in case of a uniform flow, what is uniform flow? Uniform flow is one for a given length of the channel, velocity, depth, cross-section area, slope of the channel. So they remains constant. If they are not constant, then it will be called non-uniform flow. So when in the non-uniform flow, we have further classification that is called rapidly varying flow and the gradually varying flow. Non-uniform itself is one where it keeps changing. It keeps changing for a given length of the time. The velocity will not constant. Then the discharge will not constant for non-uniform flow. When non-uniform flow, as took more classes like rapidly varying flow, you can see from the figure, rapidly varying flow means within a very short length of the channel, then flow characteristics such as velocity, they keeps on changing. So in case of a gradually varying flow, the flow characteristics, of course, they may vary, but the variation is very gradual. Now coming to laminar and turbulent flow. Like in the pipe flow here also, laminar flow is one where the Reynolds number is less than 500 or even 600. So coming to the turbulent flow. So turbulent flow in open channel is one where the Reynolds number, which is more than 2000. The most important types of the flow as far as this open channel is concerned is subcritical, critical, and supercritical flow. Then what is subcritical? There is a functional parameter called a fraud number which decides the type of the flow. Critical flow, subcritical flow, and a supercritical flow. Subcritical flow is one for which fraud number is less than 1. So that I will show in the separate figure in the coming slide. Then critical flow is one for which the fraud number is equal to 1. Then supercritical flow is one for which the fraud number is more than 1. Now CHEZY'S formula. CHEZY'S formula, and in order to find the discharge, in the open channel means our aim is to find the discharge. Why do we consider channel? Because we have to convey the water to a farmer through a designed channel. So we must know what is the amount of water or the rate of the flow you are conveying from the reservoir through the channel to the command area. So in order to irrigate the area. So there is a definite a cross section of the channel, and there is a known quantity of the flow using the formula, CHEZY'S formula. This equation is called CHEZY'S equation. Q equals AC under the root m into I, where Q is called the flow rate, and A is the cross-sectional area of the channel, where C is a constant. C is actually, which is an indicator of the roughness of the channel. So that is also called as CHEZY'S constant. That small m, which is hydraulic mean depth. That small m can be obtained by the ratio of the cross-sectional area of the flow by the perimeter of the channel. That m equals A by P. So I is actually channel bed slope. Channel is a gentle bed slope, unlike other other types. It has a very gentle slope, and that slope is called small I. Now coming to the most economical section. Simply saying the channel section or the economical section. Economical section, they have got a special character. So when we say the channels are most economical, their construction cost is always less. The cost of the construction of the channel is always minimum. Then the cost of the construction, which directly depends on the excavation and the lining. So lining and the excavation cost plays an important role as far as the construction of the canal is concerned. Now, to keep the cost down, the wetted perimeter for the given discharge should be minimum. So these are all the three important factors of a most economical suction. Now coming to rectangular channel. So you can see the rectangular channel which has a dimension width as B, depth as D. There are conditions, normally the channel having a cross section trapezoidal. Sometimes there is a rectangular, and the open channel, even it has a cross section in the form of a circular in case of tunnel. Conditions of most economical rectangular suction. So the condition number 1, when we say when the channel, rectangular channel, if it is really most economical, there is a relationship between B and D. The value of the B, that is called width of the channel, will be twice the depth of the flow. Twice the depth of the flow is not the depth of the channel. Instead, it is the depth of flow. Similarly, there is one more condition, and these conditions are very important as far as numerical problems are concerned. That m is called hydraulic mean depth. That is exactly equals to half the depth. That is exactly equals to half the depth. So when the channel is economical, so if they just give one dimension, it is enough because there is a relation between B and D. So we can also find m. Now let us see the exercise. One example on rectangular channel. A rectangular channel carries water at the rate of 400 liters per second. When the bed slope is 1 in 2000, calculate the most economical width of the channel if the CHEZY'S constant is 50. So you can see they always mention clearly whether the channel is economical or not. So sometimes it will be lined, or the cost of the construction is minimum. These are all words, they give hints so that the channel is an economical channel. So here there is an economical rectangular channel. You are calculating the economical width of the channel. The B value you are calculating. So how we can calculate? So since the channel is said economical, or you are finding economical dimension, when you are finding economical dimension, by default channel is economical. For most economical rectangular channel, we know that B equals 2D. There is a relation. Also, we know that M equals D by 2. So then, since it is a rectangular section, then area of the rectangle will become B into D. That is the area of the flow. So in place of B, we can write 2D. So because B equals 2D for most economical rectangular section. So when you write B as 2D, it will become 2D square. Area will become 2D square. When you substitute discharge, because the value of the flow discharge is given, that is 400 LPS. Rate is 400 LPS. Rate means flow rate. Flow rate means discharge. That is 400 LPS. We have to keep the flow rate in terms of cubic meter per second, because 400 liter per second means every cubic meter will be equal to 1000 liters. When the unit is in LPS, you divide by 1000, it will be converted to cubic meter per second. So now you can substitute Q as 0.4, A as 2D square, and C is given. C is a CHEZY'S constant which has no unit, just a mere number, 50. Under the root, M is D by 2, because still D is not known. I is 1 by 1000, that is the channel bed slope. The unknown here is only D. So just by solving, we can find D. The moment when D comes, we can also find B, because B equals 2D. So B equals 2D, that answer is 1.154. Your second answer is correct answer. So that is 1.154. We have to calculate carefully. You have to read the problem whether it is economical or not. When it is economical, they will ask you to calculate dimensions. They may ask you to calculate the bed slope. So they may ask anything. Now coming to the trapezoidal channel. So most of the open channels they have in trapezoidal cross section. Similarly, this one is. So there are conditions of most economical trapezoidal, like in the most economical rectangular channel. Here also we have got some conditions. So actually, most economical trapezoidal channel which has n number of conditions, but at least for problem purpose, if you know this much, which is enough. You can see the figure. The bottom width, the trapezoidal channel has a width at the bottom that is called B. And there are two sloping sides of the channel, because the shape is trapezoid. The two sides are sloping, and they used to have an equal inclination. The width at the top, which is always more, that the top width, the width at the top will be always equals to double the sloping length. Each sloping length will be equals to D into root of 1 plus n square, D into root of 1 plus n square. So that will multiplied by 2, that will be the top width. So that's what written. And there is one more condition for most economical section, M equals D by 2. It is also there in case of rectangle. So I repeat, the width at the top will be equals to this double the sloping length. It is twice the sloping length. Each sloping length equals to D under root 1 plus n square. Then what is n in the formula? That n is actually, that is the component. The n is the component of the slope. So when you just look at this, just you draw one vertical line and horizontal line through the sloping side. We always keep the vertical coordinate as 1, the horizontal component as n. For any value in the vertical side, we can calculate the horizontal component as n. So when the vertical is not a 1, this is most important when you solve the numerical problems. Because if this sometimes in the problem 1:1, which means that both vertical and horizontal are 1, so that no confusion, n equals 1. Sometimes 2 horizontal is to 1 vertical. So like that when they give, so please write those numbers in place of vertical and horizontal. This is called slope. So you always keep the vertical one, that horizontal one will be called n. So that is called the horizontal component of the slope. Now we have one example for trapezoidal section. A trapezoidal channel with a side slope of 1:1 has to be designed to convey 10 cubic meter per second at a velocity of 2 meter per second. So that amount of concrete lining for the bed and the slope is minimum. Slope means for a side is minimum. Calculate the area of the lining required for 1 meter length of the canal. This is one simple example. Here there is a canal which has a side slope of 1:1. When the side slope is 1:1, no doubt n equals 1. When the side slope is not 1:1, so for example 2:1, they clearly specify what is 2 and what is 1. They always mention like 2h is to 1v or 3v is to 2h. Like that they will mention. So accordingly we write those values in this. So we keep the vertical one, corresponding horizontal, that will be called as n. That is very important, because that is the only area where we normally tend to do mistake. 10 cubic meter per second at a velocity of 2 meter per second, so that the amount of the concrete lining for both bed and the side slope is minimum. Calculate the area of lining required. Since it is the amount is minimum, with the minimum cost we are constructing the canal, so channel is most economical. So you have to write the figure. Then side slope is, that is n is 1:1, means n is always 1. So because if you write 1 and 1, because vertical we always keep 1 bar, the horizontal one will be called n. So when vertical is not a 1, you must convert that into 1 by dividing both the values by 1. Okay. What is the vertical value? So for example, vertical is 2, then you have to calculate n. So you divide that by both the number by 2. For any value horizontal, that will become n automatically. Discharge Q, that is 10 cubic meter per second. Velocity 2 meter per second. These two are given. So since the discharge and the velocity are known, then basically discharge will be equals to A into B, area of the flow, into velocity of the flow. We can able to find the area of the flow, that is Q divided by this. We have discussed in the last session in the subject fluid mechanics. Q but divided by V, that is 5 meters square. Then the flow area of the channel is 5 meters square. So now B and the D are the depth dimension of the channel. B is the width of the channel at the bottom. D is the depth of the flow. Since the amount of the concrete lining for the bed and the side is minimum, the suction should be most economical. When you say the suction is most economical, as I told, there is a relation between the top width and the sloping side. The top width is AB, that will be always twice the sloping side A. This is AD. So AD value is D into under root 1 plus n square. It is simple geometry. D into under root 1 plus n square. You must double this value. This value is always equal to the width at the top. So we use that condition. And this condition you cannot simply use unless the suction is economical. B plus 2nd equals 2D into root of 1 plus n square. Since the n value is also known to you as 1, just substitute n as 1. You will get the relation between B and D. That will be B equals 0.828D. And as far as the trapezoidal suction is concerned, there is a formula for area, that area equals B plus ND into D. This is simple formula. B plus, if you look at the geometry of the figure, we can find this form, B plus ND into D. And the B value is known to you, just substitute, but B value is known, but which is in terms of D. When you substitute, you will get the area in D. You will get the area in D. So once the area comes, so that you find, but in the form problem, we also calculated the area as 5 meters square. The area we already found 5 meters square, but we are again getting the area as 1.828 D square, so that when you equate these two, you will get D, which is 1.654 meter. We can also find B. When both B and D of the trapezoidal section are known, the wetted perimeter. Wetted perimeter is nothing but the length AB plus BC plus CB. In a very simple way, the wet length of the channel seen in the cross section. That is the AB length, DC length, CB length. When these three lengths put together, that is called wetted perimeter. Let us find wetted perimeter first. So in the problem, it is asked to find what is the area of the concrete lining per 1 meter length. So just by knowing the wetted perimeter, and for any length when they ask, you can calculate the area of lining. Just if you find the wetted perimeter and perpendicular to the figure, you have a channel. And if you just consider 1 meter length, multiply with the perimeter with 1 meter, so you will come to know the area of the channel for 1 meter length for the purpose of lining. That's why area of lining is perimeter multiplied by length. 6.047 is the perimeter. 1 meter, since it is as per meter, that's why 1 meter is multiplied. So finally, the area of the lining 6.047. This much is the area is lined in the canal. So the answer is 6.047. The fourth one is the correct answer. Only thing is we have to remember the conditions, most economical conditions. So when the problem is not economical, so they will give both the dimensions. Now coming to the circular sections. So you can see the figure. So in this figure, the AB is actually free water surface. We can describe the circle. So the CO is the center of the circle. R is the radius of the circle. The small d is the depth of the flow, whereas this capital D is the diameter of the suction or diameter of the channel. So the flow actually for circular section. So when we will call as open circular sections as open channel, when there is a passage of air in the pipe in the circular section, then it will be called open channel. When they are running full, it is not an open channel flow. Pipe flow is called as an open channel flow provided when they are running partly. When they are running full, it will become a pressure flow. Now in the circular section, there is a formula in order to find the area of the flow. So area equals r square into theta minus sine 2 theta by 2. This formula, one should remember this formula for the purpose of finding the area of the flow. So this is actually we have to draw this figure for every problem in the circular sections by knowing the depth of flow. So if the, for example, imagine if the diameter is 2 meter, depth is just 0.5 meter, which means that the center is AB is a water surface. When the diameter is 2 meter, radius is 1 meter. When the depth of flow is 0.9 meter, means that free surface AB which comes below the center. So sometimes the free surface AB is above the center depending upon the depth of the flow. So accordingly, we can calculate the area of the flow using this simple formula. A equals r square theta minus sine 2 theta, where r is the radius. And wetted perimeter. Wetted perimeter, for any depth of the flow, we can find the wetted length using the formula P equals to r theta, where r is the radius of the section and theta is the angle subtended. Theta means at O, the angle is 2 theta. Each side is theta. So the angle between the line OB and the OA, between the line OE and OA measured at the center will be called subtended angle, that is 2 theta. That is 2 theta or theta each side. That angle is called angle subtended at the center. In this formula, when you use to calculate the area and the perimeter, you must know what is the angle at the center. Without knowing the angle at the center, you cannot calculate the area of the area and the perimeter. Without area and perimeter, you cannot calculate them, and totally we cannot complete the whole problem. Theta means in the formula theta minus sine 2 theta. The value of the theta you should convert into radian and then you substitute here. Sine 2 theta, where the value of theta in degrees. Here we are substituting the value of theta both in radian and degrees. In the place of theta, it should be radian. In the place of 2 theta, it should be degree. For converting radian, it is pi by 180 degree. Now coming to the most economical, like in the trapezoidal and the rectangular, here also we have cases, conditions for the most economical circular section. The conditions are, here there are two separate conditions, one for velocity, one for discharge. Condition for maximum velocity. For just if they say calculate the discharge of the most circular section such that the velocity is maximum. Just if that word is there, which means that the section is an economical. Using the condition of maximum velocity, you are finding the flow rate. So when they say maximum velocity or maximum discharge, accordingly we use 2 theta. This is the one condition for a most economical circular section, which says that 2 theta is equal to 250, means the angle at the center to be 257 degree 30 minutes, then only you will get the most economical section is one and which conveys maximum flow. The most economical section means which is always designed in order to carry more flow. By laying the canal means there will be no much percolation loss. So the idea is most economical section means they line the canal, they reduce the transportation loss. Then the condition for maximum velocity, 2 theta equals 257 degree 30 minutes. Even without knowing the depth of the flow, if just they say calculate the flow rate using the condition of maximum velocity, which 2 theta is 257 degree 30 minutes. It has been proved. Similarly, we also have one more condition for the most economical circular section, which is called maximum discharge. When the condition is maximum discharge, then 2 theta is 308 degree. Sometimes we use this condition, sometimes we use this condition. They will clearly state about these two conditions in the problem. Now coming to the problem. So about the circular section. Calculate the quantity of water that will be discharged at a uniform depth of 0.9 meter in a 1.2 meter diameter pipe, which is laid at a slope of 1 in 1000. Assume the CHEZY'S constant as 58. And these are all the options. Here we have a circular channel which has a diameter equals to 1.2 meter. And the depth of the flow in the channel which is more than the radius. So 1.2 meter means radius is only 0.6. So you have the depth of the flow which is more than the radius. Thereby the free line So we always, this AB inside the channel, you can see the free surface which is more above the center because you have the depth more than the radius. So now what we have to do, you can mark the center, say O. Then you draw OA, you just draw a line AB called free surface. Then join OA and OB. So then you draw vertical line through O, it will be C at AB and it will be D at bottom. Now the angle between that AOB, AOD will be called as theta. Here also theta. So actually we want this theta. So theta, since it looks like more than, when the depth of the flow is more than the radius, you always remember theta is more than 90 degree. Then what to do in such a case? Then on the other side of the theta, you can see alpha. We can easily calculate alpha. If just we can easily calculate alpha by knowing the OC length, OA length. So how? Then C to D is called depth of flow, which is 0.9 meter. Then O to D, which is called radius of the suction, which is equals to 0.6 meter. Then the difference will be called as C to O, which is equals to 0.3 meter. Then OA is called radius, which is equals to 1.2 by 2 means 0.6. So then in the triangle ACO, if you take cos of alpha, that is adjacent side by the hypotenuse, OC divided by OA, you will get alpha easily. The moment when alpha comes, then alpha plus theta will be called 180 degree. So that we can calculate, we can get theta as 180 degree. Theta is 180 degree. Now, theta plus alpha is 180 degree. Then you will get theta as 120 degree. Then 2 theta is 240 degree. We have to convert theta value to the radian, which is 2.0944 radians. The moment when theta comes, we can calculate both area and the perimeter. In the perimeter formula, put theta is in radian. In the area formula, in the place of theta, it should be radian. In the place of 2 theta, it should be in degrees. It should be in degrees. So when you calculate area, you can substitute in the discharge, and this is the common discharge equation irrespective of the cross section. Only thing is the way we are finding A, P, this varies from section to a section, but once all this comes, so finally the formula for calculating discharge will be remain same for every section. So AC into root M. A means area flow, C means CHEZY'S constant, M means hydraulic mean depth. M is called as hydraulic mean depth, that is equals to hydraulic mean depth can be calculated by the formula A by P. Capital A by capital P. That's why it's written. Then small high. So pi is the bed slope. We can then discharge will be 1.004. Now look at the answer. 1.0404 is there. That is the second answer, which is the correct answer. Now coming to specific energy. As far as the open channel is concerned, we know that the total energy in the pipe flow in the last session, total energy is one. Normally when flow takes place in a pipe which has certain energy, so the energy is the sum of 3 values. The first one is the pressure energy, the velocity kinetic energy, and the datum energy. So that will be P by rho g plus V square by 2g plus Z. That is given by the Bernoulli's equation. So now what is specific energy? Whenever the energy of the flowing liquid, which is measured keeping the channel bottom as a reference, that energy is called specific energy. Specific energy is the most important energy. So in case of a channel flow, and which is always measured keeping the channel bottom as a datum or a reference. So now look at it. So in the E equals H plus V square by 2g, there is a one missing here, that is called Z, which is called datum head, because you are measuring the from the bottom. Normally Z is the height by which the bottom of the channel is above the reference. Since the channel bottom itself is a reference, thereby Z is 0. That's why you don't have that. So if the channel bottom is used as a reference line for measuring the energy in the open channel, that particular energy is called specific energy, and which is the sum of only 2 energy. One is called H, that is height of the water or pressure rate. The other one is V square by 2g, that is called potential energy, kinetic energy. So this is sum of only the 2 energy, that sum of the 2 energy. You can see this. Now coming to the specific energy curve. This curve speaks everything in the channel flow. So actually in the previous slide, so E equals E specific energy, which will be H plus V square by 2g, where H is equal to EP. EP means potential energy. V square by 2g equals EK. If we just draw so E equals specific energy, which is equals to sum of 2 energy, potential energy and the kinetic energy. Now in the specific energy curve, you can see if you draw a curve such that EP equals H. EP equals H means the potential energy is nothing but H. So if you draw a curve EP equals H, the curve goes straight because it is directly proportional. So it has an originates through the origin with an angle 45 degree. Now if you draw one more curve for the kinetic energy, which is V square by 2G. Now that actually there is a small q here which is called discharge per unit width. So discharge can be, when you divide the discharge by the width of the channel, that will be called as discharge per unit width, which is denoted as small q. So this is called kinetic energy, which can be expressed in the form of small q. So there is a q, and actually, so along the channel bed, we have taken the energy along along the y-axis, we have taken the depth, along the x-axis, we have taken the energy. So now EP equals H means with the increase of the depth, the energy will also increase. So then E equals actually energy is proportional directly. Potential energy is directly proportional, whereas kinetic energy is inversely proportional. With the increase of the depth, the energy is reducing. With the energy is reducing. So now these are all the two curves. These two curves can fit together. It will become a single curve. That curve will be ACB, which is called specific energy curve. So just don't see the other two curve. You can see only the one single curve, which is ACB, that is called specific energy curve. In the ACB curve, the most important part is the leftmost edge will be called point C. The energy against to this point will be called as minimum energy. And the depth in the channel with respect to this particular energy will be called as critical depth. And for any other depths in the channel, you can find there are two depths, H1 and H2. H1 and H2, you can see H1 is this much. H2 is this much. And both H and G, they have at two different depths in the channel, but still they have same value of energy. So they are called alternate depths. The interesting thing in this specific energy curve is there is a point where the energy is minimum in the channel. That is called as the depth at that section is called the critical depth. And there are two depths, both they have the same value of the specific energy. That will be called as, they are called as alternate depths. Now coming to critical flow, subcritical flow, and the supercritical flow. So critical flow is one for which specific energy is minimum. So the subcritical flow, so the depth of the flow is more than the critical depth, or Froude number is less than 1. Supercritical flow, the depth of the flow is less than the critical depth, or Froude number is more than 1. And alternate depths, as I shown you in the figure, the against point G and H are the 2 points in the channel. They have the common value of the specific energy, but the depths are H1 H2. But when you can see when the depth is, if you wish to calculate the energy through this graph, so you should know what is the depth. So say the depth is H, then draw a horizontal line, you meet the graph that at H, then draw a vertical line through H, you will get the horizontal value, that is the energy against H2. Similarly, if you want to measure the energy with respect to H1, so another depth in the same channel, draw H1 means height, so then draw horizontal line, you will get G, then draw vertical line. So but both H and G, since they falls on the same vertical line, they have same energy, but the depths are different. They are called alternate depths. Alternate depth is the most important depth. Now coming to critical depth and critical velocity. Critical depth means the depth at which specific energy is minimum. So you can see in the actually this really happens in the channel. This is not a mere curve. This indicates the energy dissipating in the channel. So but C is the point in the channel where the specific energy is minimum. The depth at that particular point will be called as critical depth, and which can be found using the formula q square by 2g. Q small q is none other than the cap. When the discharge is divided by the width of the channel, that value will be called as discharge per unit width, which is commonly denoted by the letter small q. Q square by 2g by power 0.33 or 1 by 3. Similarly, critical velocity. The velocity of the flow corresponding to the critical depth will be called as critical velocity, which can be found using the formula GHC power 0.5 or root of GHC. Now coming to problem pertaining to this theory. Find the critical velocity of the water flowing through a rectangular channel of width 5 meter when the discharge is 15 cubic meter per second. Now we have a channel, rectangular channel, which has width 5 meter and the discharge is 15 cubic meter. Since the width of the channel is known and the discharge is 15 cubic meter, I told you just now, when you divide the discharge by the width of the channel, you will get the discharge per unit width. It is just discharge is 15 cubic meter. It is through the entire width of the channel 5 meter. If you wish to find the discharge of the channel per meter width, you must divide it by the present width of the channel. You will come to know that. So the discharge per width, means per meter, that will be denoted as small q. That small q will be 15 by 3 meters. When you know the small q, we can find the critical depth using the formula small q square by g 1 by 3. So small q is 3, g is 9.81. You will get critical depth. So when the critical depth is known, there is another formula for critical velocity. Vc equals the root of GHC. So just if you substitute HC value, you must find HC value first. Without HC, you cannot calculate Vc. To find HC, you have to find small q. Small q is a discharge per unit width. Then we can find Vc. Vc is 3.008. Now the answer is second one. Second one is the correct answer. You have to work out correctly. Now coming to the hydraulic jump. And this is the most important as far as the channel flow is concerned. So now you can see this is the direction of flow. So there is an obstruction in the form of a small dam. So this is just a dam, an obstruction. So this is called upstream. This is called downstream. So this is the direction of flow. This is called upstream side. This is called downstream side. What is actually happening in the channel flow? So when the water is flowing in the channel, the moment when it finds an obstruction, and it will start rising in the upstream side of the obstruction. It will start rising in the upstream side of the obstruction, and then it falls over the obstruction. This only rising, and due to which there is a transformation of the energy takes place. So that is it will be converted to from unstable shooting flow. The unstable shooting flow can also be called supercritical flow into stable streaming flow in the downstream side of the canal. So actually there is a jump of water will be taking place due to the transformation of unstable shooting flow to the stable streaming flow or subcritical flow. This is the figure indicates actually this is just for derivation purpose. Normally if you write one section, so it is just after the jump, and again then water will start rising. When it start rising after the jump, and it will reach a maximum height, and then onwards it will become constant. That's why at the specimen portion of the channel after the jump takes place are taken. So the depth one is at 1 is d1, depth at 2 is d2. The depth at 2 will be called as depth of hydraulic jump. Depth of hydraulic jump is the depth at 2 suction. The moment when it reaches the maximum height after jump taking place, that is called depth of hydraulic. During the jump, then the liquid will lose some amount of energy, that will be called loss of head. So or loss of head due to hydraulic jump, and which can be calculated using the formula d2 minus of d1 whole cube by 4 d1 d2. So the depth at 2 is called d2, the depth at 1 will be called d1, then d2 minus d1 whole to the power 3 divided by 4 d1 d2 will be, that formula will be used to find the losses. Now coming to the impact of jet on vanes. The impact of jet on vanes. What is impact of jet? Impact means it is a kind of a force exerted by the jet on the plates. And we are going to use that Newton's second law of motion, which says that F equals ma. But you can look at this figure. Now, actually in the impact of jet of vanes, we have both. Means the vane can be fixed or even they are moving. So you can see the figure. You can see the pipe. At the outlet of the pipe, there is a small part called nozzle. Nozzle is one which has a reducing cross section. Thereby, the water comes out of the nozzle from the pipe, which has a enormous velocity, and using which it will strikes the fixed plate. You can see that this is a plate which is kept fixed, and it is exposed to the jet normally. Jet has a velocity equals to v. The plate is actually fixed. The moment when the jet comes and hits the plate, then what happens? Then there will be a force exerted by the jet on the plate. After striking the plate, the water leaves the vane in both the direction along the plate. So now, in order to calculate the force or the impact by the jet on the plate, so we use the Newton's second law of motion. So F equals ma, where m is actually, that is the mass of the liquid jet striking per every second, which can be calculated using the formula rho into A into B. Mass nothing but rho into B. Rho is the density, A is the cross section of the jet, V is the velocity of the jet. A means it is the rate of change of momentum, the rate of change of velocity. That what is V1 and V2? V1 and V2 are the velocities of the jet velocities of the jet in the direction of the jet. V1 means before it strikes, V2 means after it strikes. So both are in the direction of the jet is x-axis. Initially, the velocity of the jet is in the x direction, its value is v. Finally, after striking, the velocity of the jet will remain v. It is an assumption actually. After striking, it still have the same velocity. The vanes are assumed smooth, thereby there are no losses. So, but its direction is v. But we want both v1 and v1 means before it strike, v2 means after it strike, after the striking, and F means it is the force exerted by the jet in the direction of the jet. If you wish to calculate the force by the jet in the same direction, you must keep the both V1 and V2 in the same direction. One means before it strike, two means after it strike. Since one means it is V only, two means it is though it is V but direction is Y. Its its component in the x direction will be 0. That's why it is 0 is written. Then this is the final. Only thing is you must know the theory background, how finally the rho AV square comes. So with this formula, we can able to calculate the force exerted by the jet in the same direction. So only when the jet vanes are kept fixed and they are exposed normally to the jet. In the same manner, sometimes the vane means plate. The plates are not normal. Instead, they're kept inclined. When such plates are, when the jet strikes such plates, so then we can calculate the force. F means force. N suffix means direction. N means the force exerted by the jet in the direction normal to the plate. In this direction, we can find using this formula. We can also find the force exerted by the jet in the jet direction, that is called Fx. Jet direction means this one, Fx. We can also get the component of the force in the direction normal to the plate, that is called Fn. Actually, we can find Fx after finding Fn only. So these are two formula you must remember as far as when the jet strikes the inclined plate when it is stationary. Similarly, we also have the curved cases, and in all the three cases we took the stationary. Stationary means fixed vane. When the jet is made to hit the curved vane at its center, then there will be a force exerted by the jet on the plate in the direction of x, in the direction of y. We can calculate in both the directions since it is a curved vane. So by resolving this, actually after striking, the jet strikes with V and it leaves with V. That's correct. But the moment when it leaves, it will move tangential with the curve, so it will become inclined, so that we can find its components in the y and x direction. And the jet initially it is only in the one direction, that is x. And after striking, it leaves in the two directions, they are called x and y. Thereby, we can find both the fx and fy as far as curved vanes are concerned. Now, with this background, we have a problem. A jet of water of dia 75 mm moving with a velocity of 25 meters per second strikes a fixed plate. We have to read to which particular case the problem belongs. A jet of water of 75 mm dia moving with a velocity of 25 meters per second strikes a fixed plate in such a way that the angle between the jet and the plate is 60 degrees. That is the most important. So you can see the angle between the jet and the plate, this angle. The angle between the jet and the plate is this is very important. 60 degree. Find the force exerted by the jet on the plate in the direction of the jet. In the direction of the jet means Fx. So how to calculate? Diameter of the jet is known. Using this, we can find the area. Velocity of the jet is known. Velocity of the jet means that is the initial velocity 25. Then angle between the jet and the plate, that is called theta 60 degree. Then there is a formula to calculate the force exerted by the jet on the plate in the direction normal to the plate. Fn equals rho AV square sine theta. Fn equals rho AV square sine theta. Actually, we want the force exerted by the jet on the plate in the direction of the jet. In the direction of the jet. So that value will be equals to 2390. So if you want to calculate the force exerted by the jet this is in the direction normal to the plate, this is the force exerted by the jet in the direction of the jet. That is Fx equals Fn times of sine theta. We actually calculated both, because sometimes they ask Fn, sometimes they ask Fx. So one should know how to calculate both the forces. But you have to see which is the correct answer. The correct answer is, because you are calculating force exerted by the jet on the plate in the jet direction means Fx, not Fn. Fn is only for curiosity. We can find for inclined plates how the forces can be found in the direction normal to the plate. But yeah, the real impact is in the jet direction on the plate, whether they are fixed, whether they are kept normal to the plate jet, or whether they are inclined to the jet. Now coming to one more problem on the same case. A jet of water of 2.5 cm diameter moving with a velocity of 10 meter per second strikes a hinged square plate of uniform thickness. Find the angle through which the plate will swing. Actually, the moment when the jet is made to strike an hinged plate, then it tends to swing. Then whenever the plates are hinged at the top, the moment when jet strikes, then it will have some amount of swing. That swing is actually asked to calculate the angle of swing. There is a formula: sin theta equals rho AV square by W. So rho AV square, rho is the density. Because diameter is known, we can calculate the cross section A. V means velocity of the jet. W means it is the weight of the plate. In the problem, they have provided everything. So they have given almost everything. Density is 1000 for water. A is cross section. V is the velocity. W is the weight of the plate. Sin theta is the angle through which the plate will swing. That answer is 30 degree. Now the B is the correct answer. Now coming to one more problem, and this is the most important problem. A nozzle of 50 mm diameter delivers a stream of water at 20 meter per second perpendicular to a plate that moves away from the jet at 5 meter per second. So this is actually not a fixed case. And remember, so whether it is a fixed cases or a moving cases, we cannot expect every time that plates are fixed. So the plates are keeps moving in case of a turbines. So you should know how the turbines, the principle of the turbine is. So they keeps on moving, the vanes are moving. So in this problem, how to calculate the efficiency? You can calculate the efficiency by finding the force. Since it is a moving vane, please remember the formula which are applicable to fixed vanes. They are also applicable to moving vane. With the only difference is wherever V in the formula will becomes V minus U. Wherever V in the formula, for example, rho V square for fixed plate when the jet strikes normally. In place of V, we write V minus U. That's all. V is velocity of the jet. U means the velocity of the plate, because plates are moving. When plates are not moving, we stick on to rho AV square. So likewise. So this is the problem. A nozzle having 50 mm dia, which delivers a stream of water at 20 meter per second perpendicular to a plate. The plate is also moving from the jet at 5 meter per second. Moves away from the jet 5 meter per second. Find the efficiency of the jet. So in order to calculate efficiency, there are few steps. Carefully we have to follow. Dia of the jet means we can find cross section. Velocity of the jet means that is called V. This is called V. Velocity of the plate means that is to distinguish velocity of the jet and velocity of the plate, we have to use V and U. Now coming to force on the plate. Force on the plate means Fx. Yeah, as I said earlier, so in case of a moving vane, we have to use rho A. V square means V minus U whole square. With the only difference is V is replaced by V minus U for moving vane while finding force in the direction of jet. Rho into V minus U whole square. Then you will come to know that Fx. So what is work done by the jet? For moving vanes, the work done will apply. Work done means it is the force exerted by the jet in the direction of the jet multiplied by the vane speed. So you will get the force work done. So when you get the work done unit is Newton meter per second, which is popularly called by watts. Now we can calculate the efficiency of the jet. Any efficiency basically output to input ratio. What is output? Output is actually work done in every second. Output is just like a result in the examination out of the total marks. Output is the work done. Input means that what is the energy we feed to the jet. So input means is the kinetic energy of the jet. Out of so much of energy that will going to exert some amount of work, that is called output. Output is actually visible. So output is that is a work done per second. Then input is the kinetic energy of the jet. So work done per second is actually Fx into U. Kinetic energy basic formula is half into m into v square, where m is once again m basically it is the mass of the jet, mass of the liquid striking the vane per every second. This can be found using the formula rho into A into V. In the place of m, when you write rho AV, the denominator becomes half rho AV cube. The numerator is work done, which is Fx into U. Finally, we will calculate the efficiency. That efficiency is 33.77. So your answer is second one. Now coming to the one more problem of the jet. So in this problem, what we are actually doing, there is a concept called velocity triangle. The most important as for in the hydraulics, that is the velocity triangle. Without the concept of velocity triangle, one cannot understand the principle of turbine and pumps. So what is this? A jet of water having a velocity of 40 meters per second, which is striking a curved vein, and which is moving with a velocity of 24 meters per second, 20 meters per second. The jet is making an angle of 30 degree with the direction of the motion of the wind at the inlet and leaves at an angle of 90 degree at the outlet. 90 leaves what means it is at the outlet only. Now what we have to do? We have to calculate the vane angle. So you can look at the figure. This is the most important, and you cannot calculate without drawing the figure as far as this type of the problem is concerned. So how to draw the figure is most important. So this is the shaded one is actually the plate or vein. This is the shaded one, plate is our vein, and we have to allow the water to enter the vein tangentially at one end like this. The AB indicates that it is the direction and the magnitude and the direction of the velocity of the jet at the inlet. This is called inlet. This is called outlet. P is called inlet, then E is called outlet. Jet enters through B, jet leaves through E. So how it will enters? It is entering by making an angle of some angle is given actually 30 degree. That alpha is an angle that making. Then how it is leaving? But when it leaves, it makes an angle 90 degree. It goes perpendicular. So like this it leaves. Then the rest is actually construction. The rest is the construction. Velocity triangle construction procedure is plays a very vital role in the field of hydraulics. Then how to draw velocity triangle? What we have to do after drawing the line AB, which indicates that the magnitude and the direction of the velocity of the jet, which is at the inlet. Then we have to draw an horizontal line through A. What we have to do on that line? Then you must mark a point C such that AC will be equals to, that is the vane speed, that is the vane speed. Vane speed means plate speed, that is 20. That is 20. AC is equal to vane speed. Then what is the next step? Through B, the join B and C. Then that will be called as the relative velocity. Normally, for moving vane, the difference of V and U, V means jet speed, U means plate speed. Their difference is called relative velocity. That will becomes V minus U, provided when both jet and vane are in the same direction. When the jet and vane, you can see this is the jet direction, this is the vane direction. When they are not in the same direction, however, still we can find the relative velocity through the vector difference. That's why we will construct the triangle. So what is the next? Join B and C. Then BC is called relative velocity of the V1 and the U1. V1 means initial velocity of the jet at inlet. U1 means initial velocity of the plate at inlet. Plate means this vane speed. Then draw horizontal line through B. Then you extend AC to meet D. Then you will go to a triangle which is called ABD. In the triangle ABD, each term is very important in this triangle. In the triangle ABD, the vertical side is called velocity of flow, denoted as VF1. The horizontal side is called velocity of whirl, denoted as, all suffix 1 means inlet. Here the suffix R2 indicates outlet. The corresponding values are here also. VW1 means velocity of the whirl. VF1 called velocity of the flow. These two together called as the components of the jet, real jet. They are called absolute jet. There is one more here, that is VR1, which is called relative velocity of the jet. What is relative velocity? Relative velocity is, that is a vector difference of the absolute jet at inlet and the vane speed at the inlet. Then what is the next step is, then we will go to the vertical. Once the triangle construction is completed, then everything is easy. Then, but we have to draw AB line, how jet enters and leaves, that is most important. The construction of the triangle comes next. Then draw EF line such that the jet leaves at the outlet through 90 degree. Then draw one more line EG tangential to the vane. The tangential to the vane. So such that EG equals to the relative velocity. It is an assumption the relative velocity at inlet and the outlet, they are assumed to be equal. So VR2. Then draw horizontal line through G. The horizontal line through G. Then such that GF equals to U2. Just such that GF equals to U. The G to F, which indicates that U2, then U1 and U2 are also equal. That is also one more assumption. V1 and V1 and VR2 are also equal. So with this condition, so now we can come to this. the angle made by VR1, angle made by VR1 at inlet called theta, the angle made by VR2 at outlet will be called pi. These two are together called as vane angles. Theta is at inlet, pi is at outlet. In the problem, the pi is actually asked. Pi is the vane angle at the outlet. In order to find pi, we have to follow the procedure. After constructing the triangle, there is nothing in the triangle construction if you understand correctly how jet enters and how jet leaves. That is the most important term. If that is written correctly, then automatically you will get the correct values. Now our aim is to find the angle theta which is at the inlet. So how to find theta? You can look at this. So tan in this triangle, I am talking about the triangle BCD. There is a theta here. Tan theta is equal to VF1. This side is VF1. How to find VF1 and VW1? That is also important. So VF1 by VW1 VF1. This is called VW1. That is this side by this side. That's all tan theta meaning. But BD side is called as VF1. Then the other side is CD. CD, which is actually VW1 minus V1. That's why it is written. Then what is VF1? In the triangle ABD, alpha is known to you as 30 degree and the side AB is also known to you as V1. Thereby, we can find VF1 and VW1 like this. So once that is known, you can go back and substitute, you can find theta. That is called vane angle at inlet. Once the theta comes, then we will go to the outlet triangle where this angle is called pi, that this is pi. Sin theta, in another triangle BCD at the inlet, we can also find VR1. This side we can find because this angle is just now we found. So we can find using sin theta, which is opposite by adjacent side, VF1 by VR1, we can find VR1. Once VR1 comes, VR1 and VR2, as they said, they are assumed to be equal. Once that is comes, we will go to the outlet triangle. So where this angle we are finding, that is called the vane angle at the outlet. Theta and pi are called the vane angles. Now how to find that angle? So if you take cos of the pi in the triangle EFG, if you take cos of the pi, cos pi means adjacent by hypotenuse. Adjacent side is GF, hypotenuse is GE. Then adjacent side GF, which is equals to U2, the hypotenuse equals to VR2, and both are known to you. Thereby, we can find the pi, which is the vane angle at the outlet. That answer is 36.18 degree. So your answer is the second one. The B is the correct answer. This is how we can find the vane angle at the outlet. Okay. Okay, friends. So with this, I would like to conclude and thank you everyone for your patience listening.
Thank you, Professor Mahesh. It was a very informative session. So I request participants to find the feedback link in the YouTube chat box and kindly provide your valuable feedback. And I request all the participants to join us on day 14 of our training program tomorrow on 11 December at 4 p.m. So tomorrow we have two sessions. First session on solid mechanics by Professor P.K. Umesha, followed by session 2 on steel structures by Professor Ajit TJ at 3:45 p.m. using the same YouTube channel. Thank you. Thank you all.